Next up, we'll change gears completely, and we'll go back to the basic sciences, and we'll pick up with chemistry. And I was just asking Tom whether this was true before I said it, but I think of all the talks that we've had today, maybe actually the chemists are the ones with the biggest clusters on campus. So in terms of the biggest users of computing, Tom is certainly up there when you look across campus. So all yours, Tom.
Thanks very much, Adam, and thanks everyone for the fantastic series of talks that we've had today and the great discussions as well. I look forward to telling you about a little bit of work that is going on in my group in the chemistry department. And I am a theoretical chemist, which really does fit nicely into this CS+X mode, because essentially we are interested in intrinsically molecular problems, chemical problems, but we're doing that from a theoretical and computational perspective. So the essential mode of operation that we employ is to start from the underlying equations of motion, the underlying physics that govern this overall field, which are for nuclei, essentially classical mechanics in most cases, and for electrons are essentially the Schrodinger equation. We use these underlying physical equations, we build algorithms and mathematical models to describe different chemical problems. This leads to not only interesting algorithm development, but it also leads to a variety of different software implementations of those algorithms. And then we use that software designed to work effectively on high-performance computers to investigate a range of different useful outputs, hopefully useful outputs. We work hard to make it as useful as possible. And this includes not only gaining fundamental understanding in terms of what is going on at a molecular level. It involves making testable predictions based on that understanding for experimental collaborators. And in many cases, it leads to the design and discovery of new molecular systems that have real value. And this is a mode that has a really fruitful array of possibilities. We use this approach to investigate and understand solar energy conversion, to understand key reactions that govern biological catalysis. We use this approach to investigate the way in which membrane proteins and different biological molecules are made within cells and targeted to the correct places within cells. And the story that I'll be focusing on today pertains to another project in which we investigate technological applications of these molecular systems, and particularly with focus on battery applications, where we seek to understand some of the underlying molecular processes that are making a battery work and making a battery break. And in the case of breaking, we investigate the formation of unwanted metal deposits at electrode interfaces. And in terms of making a battery work better, we investigate the actual molecular constituents of the battery with the hope of designing those that will lead to better energy density, better efficiency, and so forth. So this is an exciting and very useful way of investigating a huge array of different molecular problems. And I would really I would really emphasize that this is a field that is natural to pursue in the context of Caltech. Caltech is really a great home for this kind of work. As you can see, just from this cross-section of applications that we study, it's an incredibly interdisciplinary field. We rely not only from the algorithmic perspective on the math and computer scientists, but we have close connections with physics and biology and engineering through this work. That leads to a variety of opportunities for interesting collaborations all the way across campus that is a great deal of fun. And I'd also emphasize that Caltech has been, in many ways, the historical home for theoretical chemistry. It rests as a field on the seminal work and the seminal understanding of the nature of the chemical bond through Linus Pauling. It borrows heavily on the formulation of quantum mechanics from Richard Feynman, and there's been no shortage of Nobel Prize winners and other luminaries in the field of theoretical chemistry that have called Caltech home over the years. So this is a wonderful place to be pursuing this kind of work. Now, the specific research that I want to talk about today is a story about battery technologies. And the current state of the art for most battery applications relies on lithium-ion technologies. So lithium is a wonderful battery material because it is both a very light element and it's also an extremely electropositive element. So you can get a lot of energy per unit mass. And that is reflected when you plot a bunch of different battery technologies as a function of different measures of energy density. Basically bang per unit volume. And as such, lithium-ion batteries have become incredibly pervasive in terms of the way in which we use batteries today. They're in our phones, they're in our cars, increasingly they're in our airplanes. And there's just been an absolute proliferation of applications and success stories. But the story gets dark fast because with this proliferation of successes, there's also a corresponding proliferation of unwanted events that accompany many different battery applications. And with the Samsung recall and with boatloads of recent newspaper articles like this from the New York Times, there's clear evidence that we need better battery materials, better ways to harness that high energy density in safe manners, right? So the real culprit in terms of flammability of lithium-ion technologies is the electrolyte material. So here I'm showing the basic components of a battery. Here's the negative anode, the positive cathode, and then the stuff in the middle that allows ions to go from one side to the other side as the battery is either discharging or recharging. And the primary component of that so-called electrolyte are simple liquid organic molecules. And these liquid organics are light, they're volatile, they're flammable. So as a result, they could have limited electrochemical stability. They have that flammability that leads to the sort of problems that you saw on the previous slide. And they also require these separator layers in many cases, which demand special engineering and actually which lead to larger battery sizes than you would want for many different applications that you would like to use for different batteries. So a way to solve these various problems is to get away from liquid electrolytes and to use polymers, basically long strings of molecules that have been stitched together that lead to high mass molecules that have improved properties in some ways. They tend to have much better stability in the battery because they are so heavy and so long. They have much lower flammability, and they require less processing because of their material properties, allowing us to have much thinner batteries, opening up different applications. So this is a really exciting way to pursue different battery materials. The downside is the one point of a battery electrolyte is to get the ions through quickly, to get them from one side to the other side fast. And what we all know from the polymers that we interact with in our daily life is that they're incredibly sluggish materials, and as a result, the rate of that ion conduction simply tends to be too slow. So this is the essential design challenge. How can we get the benefits of polymers while getting fast conduction of the ions through the battery material? So historically, it's been kind of a very simple story. In the 70s, polyethylene oxide was discovered as a solid polymer electrolyte, basically as this polymer medium. Here you see polyethylene oxide. It's incredibly simple. It's just carbon, carbon, oxygen, carbon, carbon, oxygen, repeating infinitely. And this is basically showing the way in which those polymer chains wrap around the lithium ions that we want to get rapidly moving through the system. So in the 70s, it was discovered as a promising material, and today it remains still the best game in town. Basically, despite lots of work on this particular topic, there's been very little advance in terms of the overall performance of polymer electrolytes. And this has had two really interesting effects on the nature of the field. One thing is that because PEO has been the primary success, it has been the thing that we have studied by far the most. We've looked at ways to make additives, make gels, make brush configurations that lead to different forms of polyethylene oxide, but which employ essentially the same chemistry. And we haven't investigated a whole lot of alternative polymer materials. And the other really interesting thing about the success of PEO is it means that we understand the way ions move in polymers almost exclusively because of PEO. It's a very PEO-centric way of understanding how ions move in different condensed phase materials. So what does that mean? It means that we've studied things like that make PEO-based materials behave in neat, ideal fashions. For example, if we plot their conduction, basically the rate at which they move ions, as a function of their distance from the point at which they become glassy, this distance from the glass transition, they fall nicely on a line. So we basically understand the entire properties of how these ions are moving and the polymer material in terms of simple pictures like this, which relate the rate of movement of those ions to the intrinsic stiffness of the polymer, which is then a proxy for this distance with respect to which they're plotting. That's perhaps not, more detailed than one needs, but I think the take-home message that I would really emphasize is that PEO has been the thing that we have studied by far the most, and it has also been the thing that has dominated the way in which we understand polymer diffusion of ions in general. So the essential approach that we wanted to pursue was to employ non-PEO based chemistries. Can we investigate a much broader swath of different chemical possibilities in this combinatorially large space of potential polymer candidates? And can we place computation and theory at the heart of that prediction process? So what we did is we set up a multi-institution collaboration involving two different theoretical groups here on campus, my group and the chemical engineering group of Zhengkang Wang, in which we would investigate large numbers of different polymer materials. We would then pick candidates that have appealing promise. We would give those to synthetic chemists at Cornell that would then make those polymers, who would then send those polymers back across the country to Berkeley that would actually test those polymers and tell us what's working and what isn't working, and that became an iterative process. So we set that up through an NSF program a few years ago in 2014, and it's led to some really exciting work even since that time. So the basic way in which you would use computational methods to investigate the behavior of ions in polymers is a tool called molecular dynamics. And it's sort of the most naive thing that you would think to do. You basically would describe each and every atom in the system as if it were basically a system of balls and springs, as if it were a system of classical objects like billiard balls pinging around on a table. All we do computationally in this naive approach is simply integrate Newton's equations of motion by taking the configurations of the system at a given position in time, evaluating their forces, finding where they will go at a subsequent time, and then iterating this process to generate a trajectory for the overall system, to actually simulate the motion of those ions and of the polymers as a function of time. Now, the intrinsic time step that one has to take is on the order of femtoseconds for this process, whereas the characteristic time scale for the motion of the ions is more like microseconds. So the bad news is that one has to iterate this process for any given polymer on the order of billions of times in order to get even the slightest amount of information about whether or not that polymer has any kind of promise in terms of conducting the ions of choice. So as a result, when one maps out these trajectories, one does that, one generates simple molecular dynamics movies like this. One can look at the progress of, say, a lithium ion diffusing in that polymer material, and one sees that even in this kind of time-lapse movie where we're looking at billions of different configurations, very little happens because of the fact and it turns out to be an extraordinarily expensive way from computational resources to investigate this problem. And it really demands an improved way of looking at the problem, an improved strategy for looking at large numbers of different polymer materials. So what we did is we set out to achieve that sort of improved understanding. Working with these synthetic chemists, we designed a series of different alternative polymers. The details don't really matter. The point is that they're substantially different than PEO, but they have a consistent number of oxygens in them, which was useful for technical reasons. And what we did is we used that brute force approach. We used these extremely long molecular dynamics trajectories to predict the relative rate at which lithium would move through these different polymers, and we compared that to what was seen experimentally. And here's polyethylene oxide, which looks high and good, and here's all these other guys. And the agreement between theory and experiment was extremely encouraging, indicating that we can actually reliably predict these things. But the bad news is that, just like was seen from the historical evidence, all these alternative polymers are much worse than PEO, right? But the way in which they were failing turned out to be incredibly interesting. So I showed this plot earlier where in PEO-based materials, if I plotted this ionic conductivity as a function of 1 over the distance from the glass transition, everything fell nicely along a particular line. And these alternative polymers didn't behave that way. So we were failing again in a very interesting way, and it suggested that the thing that people thought was so important for determining the success of the polymer wasn't the only important factor. There was another important contribution to the overall performance of the polymer that had been missed by only studying the behavior of PEO, and that was revealed by investigating this broader class of polymers. So one can get a sense of what that was, and we got a sense by doing the following little exercise. We took a characteristic structure of the polymer. So this is polyethylene oxide, and when this is just an instantaneous snapshot of all of the different atoms in the system. And then what we did is we said, let's go through space. Let's raster through three-dimensional space, and every single time that polymer has a local arrangement of atoms that looks like what it would want to look like around a lithium ion, basically that is pre-configured to successfully bind with the lithium ions, we're going to drop a little blue ball. Boom. So this gives us a way to kind of map all of the different places that are primed to happily accommodate a lithium ion throughout the entire polymer material. And then we did that for all of these other polymers. And the difference was truly striking. Even though these polymers, from a simple molecular perspective, had nothing outstanding or nothing so substantially different than PEO, we saw that PEO intrinsically had these rich networks of places that the ions could live and highways through which the ions could shuttle along to create rapid diffusion through these different polymers. And if one looks at the density of these different edges between local solvation sites in this way, these are the different experimental conductivities, again with PEO outperforming all these other polymers, and we see that exactly the same behavior comes from the calculated connectivity of these different sites. So the point is that these solvation site networks, basically the connectivity of these networks between which the lithium could happily be accommodated in the polymer, was an important factor that was making PEO an intrinsically special material. Now that turns out to be a really useful thing. It gives us an alternative way to look at polymers in general. We shouldn't be thinking about the atoms, we should be thinking about the networks that are allowing the lithium to move through those atoms. And maybe we can actually use that to create much better algorithms for identifying new polymer materials. And that's, of course, what we set out to do. So the old strategy I showed you was simply to use molecular dynamics and run it forever to actually find out whether or not the ions moved as a function of time sufficiently quickly. An alternative strategy, and that took very long molecular dynamics trajectories that were extremely costly. The alternative strategy is to run extremely short molecular dynamics trajectories, just long enough to characterize this network of available solvation sites and to identify where the lithium could possibly be held. And then once we have those networks, we can easily model the rates for hopping of lithium ions among those networks, having a much less expensive and much more rapidly screenable technology for predicting the long time scale transport property of these different lithium ions. So we set this up, and this is an approach that we call this chemically specific dynamic bond percolation model, just because it had a catchy 40-syllable name that we liked. Anyways, so we did this, and we've been using this for the last couple of years. Now, well, actually, that's not correct. It was identified in late 2015, and we've been using it in the past year to basically begin screening huge numbers of different polymer candidates that have led to some, I think, some very exciting identifications. And the basic idea is that we can talk to our experimental colleagues. We can ask them, what is the array of different molecules that you think you can make and that you think will be sufficiently stable if you make them to be useful in battery configuration. We can take all of those combinatorially large numbers of things, we can put this into our simplified models, and we can rapidly predict the actual rate of of lithium diffusion in those different materials. So this has led us to investigate on the order of 6,000 new polymers even to date. We are able to use resources from the Department of Energy to rapidly screen across all of these different polymer materials. And actually an interesting software challenge that emerged through this overall process is that we're making lots of molecules that simply haven't been made before and for which there are not interaction potentials to describe computationally. We simply don't know for many of these molecules how they interact among each other. So we've had to develop generalized force field prediction, or basically interaction potential prediction software to enable us to automatically model all of these different potential molecules that we want to investigate. So what does that mean? It means for any given structure that the synthetic chemist predicts, we have ways of breaking that into automated ways of breaking that into composite molecules. We then do large numbers of electronic structure calculations, solving Schrodinger's equation to basically parameterize the effective interactions between the atoms in those systems, and therefore give us the potentials that we need to integrate Newton's equations of motion. This is, from a CS perspective, basically an extremely high dimensional fitting problem for which Bayesian strategies and machine learning strategies are proving incredibly useful for doing efficiently and robustly. And I'd just like to finish by telling you two really exciting outcomes that we've already had from this line of work. Here is again polyethylene oxide. Here is again the problem of how fast the lithium moves. The slope of this line is very low, indicating that there's low lithium diffusion. And basically, and the counter ion for lithium chloride salt is incredibly fast, which is also bad. We've already identified new polymer chemistries that nobody had made before, for which those two features are exactly reversed. Basically, we have 8-fold increases in the lithium conduction, which is great news. And not only that, the differential conduction with the anion is also enhanced. So our synthetic collaborators are working full out to make these new polymers and to investigate those, which we're incredibly excited about. And then another even more concrete advance has been in a collaboration of this work with JPL scientists and Honda scientists, looking not just at lithium-ion batteries, but at closely related fluoride-ion battery technologies, in which they had the need for identifying electrolyte solvents that would enhance the solubility of the ions and enable sufficient conductivity in their battery materials. And we were able, using this approach, to predict mixtures of electrolyte materials that should improve those properties. And the great news is that they have since tested those experimentally. They have identified 10-fold improvements in both the solubility and the conductivity of those electrolytes, which is really exciting. And not only that, but it has also led to vast improvements also in the cycling stability of the fluoride batteries that they're designing as well. So these computational tools are leading to entirely new chemistries that hadn't been made before and that are showing real promise that we're excited about for a variety of different battery approaches. So with that, I would just emphasize that what we have done is used computation to identify new ways of looking at how the ions move in different polymer materials. We've used those insights to develop simplified models that enable us to rapidly screen across huge numbers of different polymer materials, and which are already leading to, I think, some pretty exciting new materials that have been validated experimentally and that are leading to new technologies. So with that, I thank the people in my group who have done this work. As I said, the graduate students involved in this have been named throughout. The synthetic work was done at Cornell, and the characterization work was done both at JPL and at Berkeley. And with that, I thank you for your attention.